I will now discuss the introduction to remote sensing. Now that we've gone over the history of the camera, aerial imagery, and remote sensing, as well as the electromagnetic spectrum, I want to remind you about what remote sensing is. Remote sensing is the procurement of information about an object or phenomenon without making direct physical contact with that object. The data that is collected assigns a value to each pixel that represents a portion of the Earth's surface, kind of like color by number. So, how does remote sensing actually work? It most often starts with the sun producing light. Those waves of electromagnetic energy make their way to the surface of the Earth, where they are absorbed, scattered, refracted, dispersed, transmitted, but most importantly, reflected. The waves reflect, or not, off of the Earth's surface, and the reflected waves make their way to the imagery sensor, whether it's on a satellite, plane, or any other platform. Depending on the sensors available, certain wavelengths become recorded as pixels in a piece of remotely sensed imagery. That data is then converted to a usable form where we geographers use it to better understand spatial phenomena. There are two types of sensors, active and passive. Passive sensors do exactly what I had just mentioned. They record different wavelengths reflected from the Earth's surface. Active sensors are very similar, except they actively gather data instead of just sitting around waiting for light to enter their sensor. Active sensors emit electromagnetic waves of their own. In remote sensing, this is usually in the form of light, radio waves, or sound waves. Light waves are emitted from LiDAR systems, radio waves are emitted from radar systems, and sound waves are emitted from sonar systems. As you can see on the slide, they all end with "and raging." After the active sensor emits the light, sound, or radio wave, it waits for the wave to return and then calculates the distance between the ground location and the sensor for each pixel. This helps to create 3D images and modeling. Radar is often used to model different weather patterns. Sonar is often used in bathymetry, which models the floor of the ocean. And LiDAR most commonly is used to measure the surface of the Earth, including tree cover and things of that nature. The quality of the remote sensing data consists of its spatial, spectral, radiometric, and temporal resolutions. Spatial resolution is the pixel size of the raster image. Spectral resolution accounts for the wavelength of the different frequency bands recorded. Radiometric resolution is the number of different intensities of radiation that the sensor can distinguish between, including the number of grayscale and color shades in each band. Temporal resolution is the frequency of flyovers by a satellite or plane over an area, but it's only relevant when the data includes multiple recordings over time. A panchromatic image consists of only one band, and it's usually in grayscale. The brightness of a particular pixel is dependent on the intensity of the solar radiation reflected by the objects and then received by the detector. Multispectral and hyperspectral images consist of several bands of data. Each band can be displayed one at a time or in combination of 3 bands at once, which is called a color composite image. The difference between multispectral and hyperspectral imagery is that the number and width of the bands. Multispectral imagery usually has 3 to 10 wider bands, such as the green, red, blue, near-infrared, and shortwave infrared bands. Hyperspectral imagery has much more narrow bands, about 10 to 20 nanometers, and can have hundreds or even thousands of those narrow bands. There are a few different remotely sensed image types based on the angle of the image and how it was processed. Vertical photographs are taken from straight down. This is also known as nadir. They are primarily used for image interpretation and photogrammetry. Photogrammetry is the process of calculating distances between objects based on remotely sensed images. Oblique images are images that are taken from an angle. If the image is taken from a low angle relative to the Earth's surface, they are called low oblique, while images taken from high angles are called high or steep oblique. These images are often combined and can be done so in multiple ways depending on the purpose of the output image. Panoramas are made by stitching multiple images taken at different angles from one spot or from different spots at the same angle. Stereo imagery, which I had mentioned about my professor before, is multiple images that create an illusion of depth when they are analyzed together and they are taken from multiple spots of the same, multiple locations of the same spot are combined. In pictometry, 5 rigidly mounted cameras provide 1 vertical and 4 low oblique pictures that are used together to create imagery that shows the fronts and sides of buildings and other locations on the ground. Orthophotos, orthomaps, or orthorectified images are all the same. They are created by combining multiple nadir images that have been geometrically corrected for, removing any perspective and accounting for terrain. So by moving perspective, you will only see the top of the buildings and you will not see the side of any building. Depending on what you are analyzing, you will want to make sure that you have certain wavelength bands. I'm not going to go into detail because this is not a remote sensing class. I just want you to have an understanding about the different bands and what they're commonly used for. The coastal aerosol band, which is kind of new, is particularly useful with coastal, bathymetric, and aerosol studies because it reflects blues and violets. The blue band is best for marine vegetation with deep water imaging, and it can detect up to 30 meters down. The green band is best for monitoring vegetation because of chlorophyll. The red band is useful for monitoring tropical soils, the built environment, and geological features. It's especially important for vegetation because of how the amount of red and blue light each plant absorbs. The yellow band is not really that helpful. It just collects the quote-unquote yellowness of the objects. All red, red edge, and near-infrared short-wave infrared bands are primarily used for analyzing vegetation and moisture. The panchromatic band collects data in a grayscale image of all the visible light reflected at once into a single channel. And because it senses the most light at once, it has the highest spatial resolution. Pan-sharpening is when you increase the spatial resolution by combining panchromatic band and other band wavelengths. So if here you have your image, and sad for you, it's only 4 pixels. Now that is your green band, but you really want it to have 16 pixels for your image. So you want to double the resolution. So within that same satellite, you'll have the same picture, but just the different bands. And this will be the panchromatic band. So then whenever you overlay these images, you will now have the original 4 sections will now become 16 because if you have different values for each of these pixels. And if you have different values for each of these pixels, none of these values are going to be the same. So you are actually splitting this image and so then here, if you were to combine them, this would be 1, 1, this would be 1, 2, 1, 3, 1, 4 over here. So it starts with 2, so all these are going to start with 2, and then the order is 1, 2, 3, 4. So now instead of having values of 1 and 2, or just 1, 2, 3, and 4, you have values of 11, 12, 13, 14, 21, 22, 23, and 24. So that really increases the resolution of your images. But be careful and don't do this just so you can say that you have higher resolution data. It will not work to your advantage. Lastly, the Sirius band is used to detect clouds, and the thermal infrared bands are used to see heat, and they're most commonly used to help understand surface temperatures and in light imagery. So that is all I have for you today. Have a great rest of your week.